Okay, continuing on with our topic of acids and bases, today we're going to be talking about pH and pOH. So we're going to talk about the different factors that affect the strength of a solution. Then we're going to talk about what the pH scale is, where different acids and bases will fall on that pH scale, and then we're going to get into some calculations. We will be calculating pH, pOH, hydronium ion concentration, hydroxide ion concentration, and then we'll also be writing out dissociation and ionization reactions in order to calculate hydronium and hydroxide ion concentrations that way. So first of all, there are two main factors that affect how strong a solution is. The first is the actual concentration of the solution. So more dilute solutions tend to be less strong than concentrated solutions, but only if they are the same type of solution. You cannot compare concentrated and dilute in terms of strength when you're looking at different solutions. And that's because the more important part of determining the strength of a solution is its percent ionization. Percent ionization refers to how much of the solute, so how much of the thing that's dissolved, actually ionizes when it's in solution. So how much of that solute will actually break apart into ions. A solution that ionizes a lot will be very strong, while a solute that does not ionize will be weak. Okay, so that is the biggest thing that affects solution strength, is how much of the solute ionizes, its percent ionization. So when we compare the strengths of different acids and bases, what we're really talking about is their percent ionization. How much does that acid or base ionize or break apart in solution? So yeah, a very concentrated acid solution may be weaker than a dilute acid solution if the dilute acid solution has a higher percent ionization. So concentration is not as important as percent ionization. pH stands for the power of hydrogen, and this is how we compare acids and bases. Essentially, pH is just a way of measuring the concentration of hydronium ions in solution, which are those H3O plus ions. The pH scale ranges from 0 all the way up to 14, though some very strong acids and bases will actually go off the ends of that scale, so it is okay if that happens. Acids will have pHs less than 7. The lower the number on a pH scale, the higher the concentration of hydronium ions. And then bases will have pH values greater than 7. The higher the number, the lower the concentration of hydronium ions, and the higher the concentration of hydroxide ions, which are our OH negative ions. And then neutral solutions, of course, have a pH of 7. So this is a pH scale, and it just has a couple different examples of acids and bases. So stomach acid is very acidic, which is why it has a pH of about 1, compared to, say, tomato juice, which is not as acidic, but is still a weak acid with a pH of about 4. Pure water would be neutral. Something like baking soda would be a weak base. Soapy water, more of a mid-strength base. And then something like drain cleaner, very basic. pH is a logarithmic scale, which means that each pH value corresponds to a 10 times change in the concentration of hydronium ions. So something that looks like a relatively small change on the pH scale is actually a really large change in the concentration of hydronium ions. So for example, if you compare, say, a solution with a pH of 3 compared to a pH of 6, that's a 1,000 time difference in the concentration of hydronium ions. So yeah, just keep that in mind. The concentration is once again measured in moles per liter, and we sometimes represent concentration using those square brackets. So if you see at the bottom there, it has H3O plus in square brackets. That's how we represent the concentration of hydronium ions. There are two different formulas that we can use to calculate pH. The first is that the concentration of hydronium ions is equal to 10 to the power of the negative pH value. We won't be using that one very often though. More often we will be using the second pH formula, which is pH equals the negative log of the concentration of hydronium ions. Keep in mind, even if you're using bases, you cannot use the concentration of hydroxide ions in a pH formula. You must use the concentration of hydronium ions. So if you're given the concentration of hydroxide ions instead of hydronium ions, you can convert between the two using this formula at the bottom here. 1 times 10 to the power of negative 14 equals the concentration of hydronium ions times the concentration of hydroxide ions. So you will see in a little bit that there's actually an easier way to convert between the two. I'm actually going to come back to this when we look at the other formulas that we can use to convert between pH and concentration of hydroxide ions. So pOH is very similar to pH, only it measures the concentration of hydroxide ions instead of hydronium ions. So OH ions instead of H3O+. Bases will have higher concentration of hydroxide ions. All bases produce hydroxide ions in solution. And acids will have much lower concentrations of hydroxide ions. They have the hydronium ions instead. So these are the two formulas that we can use to calculate pOH. Again, the first one we're not going to use a ton. The concentration of hydroxide ions is equal to 10 to the power of negative pOH. The second formula here is the one that we'll be using most of the time. pOH equals the negative log of the concentration of hydroxide ions. So pH and pOH have almost identical formulas, except that pH uses the concentration of hydronium ions and pOH uses the concentration of hydroxide ions. And then this formula at the bottom is also super useful. pH plus pOH equals 14. So if you calculate the pH, you can convert it to pOH using this formula or convert from pOH to pH. That's what that formula at the bottom is usually used for. And that's the formula I prefer to use rather than this one that we saw earlier at the bottom of this slide. I find pOH plus pH equals 14 much easier to use than this formula here. And so I'll show you how to use that formula instead. Okay, so now that we've looked at all of those formulas, let's try some practice questions. Okay, so the first question asks, what is the concentration of hydronium ions if A, the pH is 4, B, the pH is 11, or C, if the concentration of hydroxide ions is that? So we're going to be using our formula. The concentration of hydroxide ions is 10 to the power of negative pH to solve these first two. So all we're going to do for A there is type into our calculator 10 to the power of negative 4, since the pH is 4, and you should get 0.0001. We'll do the same thing with B, only we'll plug in negative 11 for our pH, and you should get 1 times 10 to the negative 11. Okay, those are our concentration of hydroxide ions. For the last one here, we'll have to use the other formula. So for this one, let's just go down to the bottom here for a second. Okay, so for this one, we'll use the formula. Sorry, can't get that to balance. Okay. 1 times 10 to the negative 14 equals the concentration of hydroxide ions times the concentration of hydronium ions. And then we plug in the concentration of hydroxide ions that we were given in the question, which is 1.4 times 10 to the negative 8. And then to solve for the concentration of hydronium ions, we divide by 1.4 times 10 to the negative 8. What we do to one side, we have to do to the other. And if you type that all into your calculator, you should get this number here. Which is 7.14 times 10 to the negative 7. I get that by moving the decimal place 7 spots over so that it's right behind the 7 there. That's how we put it in scientific notation. Okay, so that's your answer to 1C. Next step, it asked us to calculate the pH. That was the second question on that page. Calculate the pH, gave us a couple different scenarios. So if it gives us the concentration of hydronium ions, we just plug that into pH equals the negative log of the concentration of hydronium ions. So we take the negative log of 0.001, and you should get 3. So that is that one. And then the other one, if it gives you the concentration of hydronium ions instead, you could, if you wanted to, use this formula to convert to the concentration of hydronium ions. But the easier way is to actually use our pOH formula. So pOH is the negative log of the concentration of hydronium ions. So we'll just plug in that concentration. I think that's a 7. Okay, sorry guys, I'm actually going to turn this into just a 7, just so this works out nicer for us. So we'll start with the concentration of hydroxide ions is 3.4 times 10 to the negative 7. If we plug that into our calculator, so negative log 3.4 times 10 to the negative 7, you'll get 6.47-ish as your pH. And then it did ask for the actual pH, but the easiest way to do that is just do 14 minus our pOH. So 14 minus 6.47, and you'll get 7.5 as your pH. Okay, so that's it for the pH calculations. Let's try the pOH calculations now, which are going to work very similarly. Maybe try these ones yourself first and then double check with what I'm about to show you. Okay, so the first question asked us to find the pOH if the hydroxide ion concentration was 9.2 times 10 to the negative 3. So I'm just going to plug this into my pOH formula. So pOH equals the negative log times the concentration of hydroxide ions. I'll plug in my concentration of hydroxide ions, and if you put that all in your calculator, you should get a pOH of 2. Then the second question asked us to find our concentration of hydroxide ions. First, if our pOH was 12. So I'm just going to plug this into my hydroxide ion concentration formula. So hydroxide ion concentration is equal So 10 to the power of negative pOH. So we'll write it as 10 to the power of negative 12. And our concentration of hydroxide ions is just 1 times 10 to the negative 12. The second question is a bit trickier because it gives us a pH instead of a pOH. So it tells us the pH is 8. The easiest way to solve this is to just figure out what the pOH is by taking 14 and subtracting the pH. So 14 minus 8 is 6. Now I can plug that pOH of 6 into my hydroxide ion formula. So my hydroxide ion concentration is 10 to the power of negative 6. That's my pOH, which gives you this number, 0.000001. Okay, the last thing we're going to look at is how to do pH and pOH calculations that involve the mole ratio. So of course, anytime we're talking about the mole ratio, you always have to start with a balanced chemical equation. If we're dealing with strong acids and bases, we're going to assume that the strong acids dissociate completely. Strong acids will ionize completely, strong bases will dissociate completely. So that means that if you're given the concentration of the acid or base, we can then determine the concentration of hydronium and hydroxide ions using the mole ratio. So if you have a strong acid, you'll start by writing out the ionization equation. If you have a strong base, you'll start by writing out the dissociation equation. Then, of course, you have to balance your equation, and then you'll just do a mole ratio to convert between the concentration of either the acid or the base, and then the concentration of either the hydronium or hydroxide ion. So then you'll just solve like that. And then once you have your concentration of hydronium or hydroxide ions, you can then use that to calculate either pH or pOH. So there are some calculations that we're going to do with that. I will come back to that in a moment. But you will sometimes have to take an extra step where before you can calculate your concentration of hydronium or hydroxide ions, you first have to calculate your concentration of the acid or base. So to do that, you may need to use C equals N over V to find your concentration. And if you don't have moles, you might have to start with moles equals mass over molar mass. Okay, so this can be a lengthy process to get a pH or pOH if all you start with is like a mass and a volume. Okay, so we'll try some calculations that look like that as well. I actually think I'm just going to do these calculations that involve all of the tricky steps. I'll walk through one of these with you, and then you should try the other one on your own, and then go back and see if you can work out the easier ones on your own, and I'll show you the answers to those too. Okay, so the first question says that we have 65 grams of sulfuric acid in 1.3 liters. It wants to know, what is the pH? So our first step is to write out the ionization reaction of sulfuric acid. Sulfuric acid, that is a name that you now have to know the formula of. Because it ends with acid, this is a traditional name. The ic ending with no prefix tells us that this is a normal state polyatomic acid, and it is H2SO4. If you don't have all your naming memorized yet, make sure that's something you're continuing to work on. Because it's an acid, it is going to react with water to produce hydronium ions and our SO4 minus 2, that polyatomic ion. Then we need to make sure that this is balanced. So I'm going to put a 2 here and a 2 here to make sure that it's all balanced. Okay, from there, now that I have my balanced chemical equation, I'm going to figure out what is the molar mass of my sulfuric acid. So I'll grab my periodic table. I'm going to have the mass of oxygen, which is 16 times 4, because there's 4 of them. plus a sulfur, which is 32, and then plus 2 hydrogen. And that'll get us a molar mass of 98. So that was my second step, was to find my molar mass. Step 3, I do moles equals mass over molar mass and divide those, which gets 0.6633 moles of sulfuric acid. Now I can figure out what the concentration of my sulfuric acid is using C equals N over V. So I will plug in my 0.6633 moles as well as the 1.3 liters I was given in the question and divide, which gives me a concentration of 0.51 molar. That is my concentration of sulfuric acid. Now, to find the pH, I don't need my concentration of acid. I need my concentration of hydronium ions. So step 5 is set up a mole ratio between my acid and my hydronium ions. The mole ratio is a 1 to 2. We use a 1 anytime there's no coefficient in front of our compound. So a 1 to 2 ratio. Then we plug in our concentration of our acid and cross multiply to solve for the concentration of hydronium ions. So 0.51 times 2 is 1.02. That is our concentration of hydronium ions. And now our last step, we can find pH by taking the negative log of the concentration of hydronium ions. So we'll plug our 1.02 into our formula and solve. And we get negative 0.0086. So it is a pH of about 0, right on. So it is a very, very, very strong acid that we're dealing with. Okay, the next question asked for the pH of SrOH2. Because this is a base, it is not going to ionize, it's actually going to dissociate, which means that it doesn't react with water, it just breaks apart into the different ions. So we'll get our hydroxide ion and our strontium ion. And then we have to balance it because we have 2 OH here, I have to put a 2 in front of the OH on my product side. Then, after I have my balanced equation, I'm once again going to start by finding my molar mass. Strontium has an atomic mass of 87.62, and then we have 2 oxygen, which have atomic mass of 16 each, and also 2 hydrogen, which have an atomic mass of 1 each. So we should get 121.62 as our molar mass. Step 3, once again, do moles equals mass over molar mass. We were given the 62 grams in the equation, so we just divide that by the molar mass that we just calculated and get 0.5098 moles of strontium hydroxide. Then we can find our concentration of strontium hydroxide using C equals N over V. We just calculated our N value and we were given the 0.9 liters. That gives us 0.5664 moles per liter as our concentration of SrOH2, strontium hydroxide. Once again, when we're finding pH or pOH, this concentration of our acid or base alone is not useful to us. We have to use that to figure out the concentration of hydronium or hydroxide ions. So step 5, set up a mole ratio between your acid or base and your hydroxide or hydronium. So in this case, our strontium hydroxide and our hydroxide ion. It is once again a 1:2 ratio. And I'll plug in my concentration of my base and solve for my concentration of hydroxide ion. And I should get 1.133-ish moles per liter as my concentration of hydroxide ion. Now that I have that, you can either convert this to your concentration of hydronium ions, or what I find easier is calculate pOH, which is the negative log of the concentration of hydroxide ions. So I will plug in the number I just found. And I get negative 0.054 as my pOH. By the way, a lot of people forget this step. They just plug in this hydroxide ion concentration right into the pH formula. Remember, pH needs hydronium ion. Hydroxide ion can only be used with pOH. But now that we have pOH, we can go on to step 7, which is calculating our pH by just taking 14 and subtracting our pOH. So 14, take away negative 0.054. We are going to end up with 14.054. So a pH of about 14, a very strong base. Okay, last but not least, the answers to the questions on slide 13. It asked you for the pH of a hydrochloric acid solution that has a concentration of 0.9. So I start by writing out my ionization. It's a 1:1 ratio between my hydrochloric acid and hydronium ions, which means there's a 0.9 molar concentration of hydronium ions. I then plug that into my pH formula and get a pH of 0.046. For the second question, it asked for the pH of a sodium hydroxide solution with a concentration of 0.7 molar. Again, I start with my equation, though because this is a strong base, it will dissociate instead of ionize, so no water needed. Once again, I have a 1:1 ratio between my base and my hydroxide, so I will have 0.7 molar for my concentration of hydroxide. I plug that into my pOH formula first and get a pOH of 0.155, and then subtract that from 14 to get a pH of 13.845-ish. Question 3 asked for the pOH of a barium hydroxide solution with a concentration of 1.2 molar. This time when I write out my dissociation reaction, I do need to balance it. I now have a 1:2 ratio of base to hydroxide ion, which gives me 2.4 molar as my concentration of hydroxide ion. I plug that into my pOH formula. So pOH is the negative log times the concentration of hydroxide ion, and I get a pOH of negative 0.38. And then the last question was a little bit different. It asked for the concentration of hydronium ion in a 0.8 molar solution of calcium hydroxide. Once again, I start with my balanced chemical equation. This is a base, so it's going to once again dissociate. I have a 1:2 ratio between my calcium hydroxide and my hydroxide ion. So I have 1.6 molar as my concentration of hydroxide ion. I then plug that into my formula, that is 1 times 10 to the power of negative 14 equals the concentration of hydronium ions times the concentration of hydroxide ions. And when you solve that formula, you should get 6.25 times 10 to the power of negative 14. For any of these questions, if you're getting something different than me, please let me know. I could easily have made a mistake. And if you're making a mistake, I will happily help you find it. That's all. Thank you so much.